So we'll be looking at principle of superposition. So this principle of superposition is the basis for theory of structural analysis. That is, we'll be considering the way the forces are being positioned, how we calculate the total summation of forces in our structure. That is the summation of forces along the vertical point or summation of forces along the horizontal point, and likewise the summation of moments about a particular point under consideration. So looking at this, there are two requirements that must be imposed on this principle of superposition. The first one is that we must believe that the material, they have linearly elastic situation, that is, they obey Hooke's law, and the load is proportional to displacement. And the second principle or the requirement is that the structure's geometry, it doesn't change when the load is being applied. That is, it has the same geometry. Let me put it that way, because if the geometry changes, then this principle will not work. Let us these are the three major equations: summation of forces along x axis, summation of forces along y axis. This 6. When we look at 6 global equation, this is for a structure that is having points x, y, and z, a 3D object. So we consider the summation of forces along the x-axis, along the y-axis, and along the z-axis, and likewise the moment at each of those points too. So, but the major one that we are going to look at for a two-plane object is this particular one. We have a summation of forces along x-axis, summation of forces along y-axis, and summation of moment about a particular point. So you can read the notes on that. It's very simple. Now, looking at this particular free body diagram, let's say the object is being cut at this particular point, or we made a cut at this particular point. What happens where the cut is being made? At each particular point, the three resultant forces will take place: the shear force, the axial force, and the moment. It will take place at each particular cut section of the member or each segment. So, but there's something that is that I want us to take note here, is that looking at if we are considering this side of this particular cut, you can see that the moment is pointing downward. The moment is pointing in this direction, let's say in anti-clockwise, and the axial force is pointing in this direction, pointing towards from the left hand to the right hand side, and the shear force is coming downward from up to down. Now, if this is the condition we are putting for this particular end, the other end will be having the reverse or the opposite of what we have here. That is, the moment at this other side, it will be clockwise, unlike this other one that is anti-clockwise. The axial force will be moving into the from the right hand side to the left hand side, and the shear force will be moving from down to up. So what it means is that when we are considering this one, what we have here, the opposite will be at the other end to have an equilibrium. Is very important. So as I always explain, you can use the sign convention. I've explained sign convention for us, and that is, if you are considering a particular scenario, if you are saying this side is this direction is positive, you have to consider it as positive or true. And if you are taking that as negative, you have to consider it as negative or true. Not that you will change it at the middle of your calculation. Is very important. So for this particular one, we said we need to establish a sign convention, and we have to define their positive and their negative values. As I said, it's arbitrary. So now let us look at I don't need to go. You can read this one. It's still the same explanation I've made. The procedure for the analysis, that is, how do we analyze this structure? The first thing is that we have to make sure we calculate our support reaction. we say before the member is cut or sectioned, it may be necessary to determine the member's support reaction so that the equilibrium equation are used only to solve the internal loadings and the member that is sectioned. Now, if the member is part of a pin connected structure, the pin reaction can be calculated or determined using the method of section. I will explain those section method later. Now, after doing the calculating the support reaction, we draw the free body diagram. Then we in the free body diagram we will locate the shear force, the bending moment, and the axial force. So the next thing is that we calculate our equation of equilibrium. So, which is very simple. This particular case, I deliberately put this one there. Though we'll start with a simple one, then we'll come back to this. Now let us look at this scenario we have here. For this scenario, let's say we have a wonderful beam that is supported in this position A to B, and it is loaded in a gradually let me say it's not the same uniformly distributed load. It's a gradually decreasing or increasing uniformly distributed load. So let us look at it in this way. How do we treat this particular case? When we have a triangular loading, the centroid is always at the, let me say, 1/3 from the light point to this place, or 2/3 from the lower point to this place. The centroid of this particular object is somewhere around there. So when you put that in mind, you will understand why you must resolve, or you resolve the UDL to a point load. The point load will be acting at this particular point. Now let us look at this particular case. How do we convert this to a point load here? So to convert this to point load is very simple. Just treat it like a triangle. We use the same formula for area of a triangle, which is half base times height. So for this particular one, half times the base is 6, the height is 45. So half times 6 times 45 will give us what? That will give us 135. So that 135 will be acting at this particular place, at this 1/3 from here to here, and 1/3 from here to here is just 2 because the whole length is 6. So 1/3 of 6 is 2, and the 2/3 is 4 meters from this particular point. So we have 135 acting at this particular point. Let me quickly erase what I have here. So let's go to the next point. So replacing the distributed load by distribution and calculating the reaction, we use this. We already know what it is. I believe we know how to calculate. If we have this, we know how to calculate the reaction at each particular end. Okay, it's very simple. To calculate the reaction at this particular end, the same thing I can divide this into ratio 1 to 3. Sorry, 1 to 3 and 2 to 3. That is, the 2 to 3 will be at this point, the 1 to 3 will be at this particular point. What am I trying to say is that there are two ways of going about that. I can say I'm taking moment to this particular point. If I take moment to this particular point, so I can now say this reaction here, I don't know the reaction yet. This reaction here times this distance is the same thing as this force, because this one is the same as this force times this distance. That is 135 times 2 is the same as maybe RS times 6. So by the time you do your calculation, you will get this RX, and then you can now apply this principle of superposition that says summation of forces along the y-axis equals to 0. So what it means is that all the forces coming down should be equal to the sum of the forces going up. So if 135 is coming down and 45 is at this point, what is the other force to balance this beam? It's 135 times minus 45, which is 90. So 90 will be going up here, 45 will be going up here. Then as 135 is coming down, so that will give us that reaction. You can do that calculation and confirm whether you arrive at this. If you didn't get this, please don't hesitate to send message or comment to my at the end of the video, so that I can explain better if there is a need. So let's go to the next point. Okay, this is the calculation. 2 divided by 6 times 45 will give us 15. That 15, sorry, let's say we are considering point C for this particular one. We are considering point C. So this segment AC will be considered, since it provides the simplest form. Now the weight at this point C will be equal to 2 divided by 6 times 45. That means it's 15. If we are considering this one here, from these 2 meters, it will be 15 here. Now this 15, this is the load in 15 to this point, but I told you the other time that the point load will be acting at 2/3, which is at this particular point here. So 15 kilonewton. Then we can also calculate the reaction and see what is happening at this particular end here. So I said the other time, at when the whole span was 6 meters, 6 divided by 6, we have times 45, we have the load to be 45 kilonewton per meter. However, when the load is at 2 meters, it's 2 meters divided by 6 meters times 45 will give us the load at 0.2 meters. And if it is 4 meters, at 4 meters will be 4 meters divided by 6 meters times 45. That one will give us maybe 30 kilonewton. So depending on what we are considering. So for this particular case, we are considering point C, which is 2 meters from this point here. So the calculation is what we have here, and then we want to now look at what is going to happen at this particular point here. When we have 15 here, what will be the shear force at this particular end? It's very simple to calculate. Since I told you we are going to use the equation of equilibrium, summation of forces along y-axis should be equal to 0. So if the whole force is we have 45 here from our calculation the other time. 45 is at this point here, and we have 15 at this place. What will be the force to make it balance? It's just a matter of removing 45 minus 15 minus VC will give us 0. This is VC. You know, I told you the other time that depending on the sign convention you are using. For this particular one, we are saying we are using downward arrow for this particular eye. So when we're considering the other side that is being cut, it will be pointing upward. So for this particular one, we have VC to be 30 kilonewton, and then we want to look at what's the second state is getting the moment at this particular point. It's very easy to do. All we just need to do is to get the moment at this particular point, you say summation of moment about point C to be equal to 0. So what is our sign convention? Our sign convention the other time we said this side is going towards anti-clockwise. Okay, so let us see what maybe that was updated here, but if it's otherwise I will okay, sorry, we have it here. They said anything going in this direction. Please, what this one means is that if it's moving in this direction, which is anti-clockwise, it is positive. So now let us consider this particular member. I want to take moment to this particular point here. So how do we go about that? We start from this particular member here. Now this member, if you want to take its moment to this particular point, it's going to travel in this form. You know, it's moving like this to this point. Now this direction is it clockwise or anti-clockwise? This is clockwise, and what we have here is anti-clockwise will be positive. So but what we have here is clockwise, so that means it will be negative. Minus 45 times what distance is this 45 going to travel to this point? It's traveling 2 meters. That's why we have 45 times 2. Now why are we saying 45 times 2? You know, your moment is force times perpendicular distance. So this force, which is the 45, the perpendicular distance is going to travel to this particular point where we are taking into consideration is 2 meters. That's why we have 45 times 2. So I believe that is clear enough. Now let us look at the second case. The second scenario is this particular force, because there's another force. We'll continue to do the same if there's any force that is on this particular beam. However, there's no force on this beam till we get to this particular point where we have this particular load 15 kilonewton acting at this point, which is 2/3 to this particular sorry, 1/3 to this particular place and 2/3 to this edge. What is the 1/3 of 2 meter? That is, the 1/3 of 2 is, I think it's 0.667. Yes, I think, yeah, 0.667. So this load 15 multiplied by this distance, but this one is moving like this, which is anti-clockwise, and we said anti-clockwise is positive. That is why we're having plus here, plus 15 that we have here, times this distance 0.667. Now it's continuing to, so there's no other force, but we are now going to add our moment about point C, moment plus moment about point C to be equals to 0. So we now make MC to be set of the formula so that we'll be able to know what we have left. So this time around, if I take this one to this side, we have 90 minus this. At the end of the day, our moment about point C is 80 kilonewton meter. So you can do the calculation and check if there's any problem concerning this. You can always hit me up so that I can explain further, or you can put the message on the comment section. Thank you. Let's go to the next phase. So this principle that we have explained is what we are going to be using, and we have tried a varying load. Yeah, a varying load. We have tried it. So the same, if it's the varying load is still let me say, other than a simply supported or uniformly distributed load. So I think that is a better example to use for this particular case. Now let us now look at what we have here. All these ones you can read this note. They are self-explanatory. So now looking at this particular beam, you can see we have uniformly distributed load from A to B. We have a point load at point C, and we have the where we want to determine. Okay, let me just read it so that we know what we want to do here. They said coordinates x1, s2, and s3 have to be used to describe the variation of the shear force and the moment throughout the length of this beam, and it's only valid for A to B, that is for x1, and from B to C it is only valid for s2, and from C to D we'll be considering distance s3 alone. So what does it mean? That is, when we're considering this particular A to B, is this distance x1 that we'll be using to, let me say, to describe what is happening in this A to B. And when we're considering this point load, it is this distance s2 that we'll be considering. And likewise, from this place to this place, we'll be using distance s3. So let's move ahead. So the procedure of analysis is like the S, which is the distance, position S, will be describing the variation of those shear force and the bending moment as they move along that particular beam. And then we'll calculate the support reaction of each particular support. Then we'll specify the shear force and the bending moment, and then we'll look at the same way we treated the other beam. It's the same thing that is applicable here. Now looking at this example we have here, we want to look at we want to determine the shear force in this beam. We want to look at it. We want to determine the shear force and moment in this beam, and this beam is just a replica of the other one. So for this particular scenario, we want to look at how this load will vary as this distance, along this distance s. How do we consider it? The same thing we did the other time. Instead of using 2/6 the other time that we are using, we'll be using x. Instead of this 2, we'll be using x over the same distance. This is the final distance. The same thing is applicable, which is very simple. We just have to just use for this particular one, we look at it. Okay, at what distance are we considering? So let's look at this case. We want to look at the support reaction. How do we find the support reaction? It's very easy. This load times this distance, this 10 times 3 will give us 30. So what will this segment carry? What will this segment carry? As I explained the other time, this segment will carry 2/3 of that, even though it's 1/3 distance, but carry 2/3 of the load, and this side is 2/3 distance but carry 1/3 of the load. So what's the 2/3 of 30? That's 20. So 20 kilonewton will be acting here, while 10 kilonewton will be acting here. So, and let me see. I'm coming. Let us look at it. So for this case, we were had to determine the shear force and moment as a function of x, So it might be a little bit different from that, but you already know how to know the final value of that. But let us let us consider it as a function of s. Now, for the purpose of calculating the support reaction, the distributed load is replaced by its resultant force of 15 kilonewton and as shown in 4.6b. Now, 15 kilonewton. Should it be 15 kilonewton? No, I don't think that should be 15 kilonewton. Why? Because it's gradually increasing load. It's not a point uniformly distributed load. If it's a uniformly distributed load, we can just say 10 times 3, then we have 30, then we can say half here. But this particular one is not so. So there's I disagree with this a little bit, but let us look at the calculation. Let us do the calculation ourselves and find out what it is. So let us do the calculation ourselves. We said this is a triangular loading, so we have let me take my pen. We have half times, what's the base? 3 times, what's the height here? 10. So we can say 2 here 1, 2 here 5. So we have 5 times 3, that's 15. Sorry. We have 15. So that means it's 15. So that means it's correct. So let's go ahead. So the total resultant force is 15 kilonewton, and I told us the other time that it will be acting at 1/3 from this edge. So we are having 15 kilonewton here. So now, having 15 kilonewton, what is the load here? What are we going to have here? Now, the 2/3 of this span 3 meters is 2. So from here to here is 2. So we have it this way. Now, we looking at a free body diagram, we believe that there's no load here first, because this is the point load. To make this one to be in equilibrium, we have to say, okay, the summation of forces along the y-axis is equal to summation of forces along the x-axis. So that's why we are taking this one to be 15 kilonewton here first. So and we are told to represent it in along the using x, using function of x. So what we are going to do is that we're going to say w divided by x is equals to 10 over 3. That is, w divided by x equals to 10 over 3. And if we are going to do that, w divided by x equals to 10 over 3. Now we can make w the sort of formula, which is equals to w will be equals to 10 times x all over 3. So the result of the dual law is this. So we can now say summation of forces along the x as y axis equals to 0. Now, if we want to look at this now, we can say 15 minus half times whatever distance we are considering, distance of x. You know, we say our w is 10s over 3. So half times minus half times what's the distance s we are considering, minus v equals to 0. So v equals to 15 minus, when you do this calculation, you have you know, taking v here, you can have 15 minus what is this, 10 times 1, 10 divided by 6, that's 1.667 s squared. Now this is the function that will be representing this shear force here. So what how do we go about using this particular expression? So for instance, if we are considering distance s to be equals to 1, all you just need to do is just change this one to 1. If we are considering distance s equals to maybe s equals to like this, now we are considering x over 3, just change s to be equal to s over 3. It will give you what you are looking for there. So let's proceed and use this and see what it's going to give us. So we have calculated the shear force, which is this is the equation that is helping us to determine the shear force. How about the bending moment? So the same thing applicable. We look at we'll generate equation for the bending moment. There's a summation of moment about point S to be equals to 0. Now, how do we go about that? We're going to look at it this way. This one is force times perpendicular distance. That's why we have 30, 15 times 2. That's why we have 30 kilonewton here. So now if we have a moment of 30 kilonewton meter here, we have shear force of 15 here. I want to take moment about point X. We don't know that point X. Let's just cut an imaginary point X. Let's say X is any distance along here. We don't know it yet. So how do we determine that? Now we can say this shear force. We'll first start with the moment. What's the direction of our moment? We said this one is positive. So if this one is coming in this direction, it is positive. We have 30, which is positive, plus 30. But because it's a moment, we are not multiplying the moment by distance. However, when we now move to the shear force, which is this shear force towards any point here, it will be moving in this direction, which is clockwise, which will now be negative. We now have minus 15 times, what is the distance? X. 15 times X. Now we continue to move. This is where we have the next loading, and we have expressed this loading as a function of half times 10 this shear force half. This shear force as half times 10 over 3x times x in our expression. Now this particular one, we multiply it by 1/3 of whatever distance we are having here. That's why we're saying multiply by this one, multiply by x over 3, because it's 1/3 of x they are going to use to multiply this, then plus the moment here. I don't know, maybe you can do the write-up on a sheet of paper and see what I'm talking about. Let me remove this so that it doesn't. So the expression is very simple. The moment here minus this one, we continue to move. This force times perpendicular distance, x, minus this minus this times perpendicular distance, plus this times perpendicular distance. And this is the shear force that is explaining let me say this is the expression that is explaining the shear force as we have here. That's the one explaining the shear force here, don't forget. So times its own perpendicular distance. Now the perpendicular distance is 1/3 to this side. If it's to this side, it is 2/3. So that's why we are using x over 3. 1/3 of x is x over 3. That's why we are having it here. So if you open this equation, we're going to have taking this one to this side will be minus 30 plus 15s minus this expression times this will give us this. So s times s times s cube. So this is the moment equation that will be explaining whatever we are having here. So this can be checked by noting that the mds equals to v and the vds equals to w. You can do that calculation yourself and then see it out. Please, I want us to try and write it out and do the write-up. Feel free to ask questions in the comments and any area that is not clear enough so that I can explain better.